Let's build our high-speed line follower program using block programming this time instead of Python. In the last video, we implemented the dynamic base power concept in Python, where the robot drives at maximum speed along easier sections of the line and automatically slows down during curves. We saw that it could keep looping around the line follower sheet without veering off. Today, we'll use that Python program as a reference and recreate it in blocks. Our Python program had two main parts, a helper function called clamp and the main line following program that combines proportional control with the slow down during curves feature. Let's start by rebuilding the clamp function in blocks. Under my blocks, choose make a block. We'll name this block clamp and then add three number inputs: power, min power, and max power. In Python, our clamp function returns a value. But in block programming, our custom block cannot directly return a value in that same way. So the workaround I'm using is to create a variable called clamped_power. Whenever the clamp block runs, it updates that variable. Then, back in the main program, we can use clamped_power as the result of the clamp operation. The clamp logic itself is the same as in the Python program. If power is too low, meaning it is less than min power, we set clamped power to min power. If power is too high, meaning it is greater than max power, we set clamped power to max power. Otherwise, the power is already within the expected range, so we simply set clamped power to the original power value. Now let's move on to the main program. As always, we'll start the program when button B is pressed. We have the same initializations as in the Python script. I've created variables for max base power, minimum base power, KP, and slowdown, and I am using the same values as before. Next, we start the loop. This loop keeps running until button A is pressed. Once we exit the loop, we stop all motors so the robot stops moving. Inside the loop, we first get the deviation from the Quad RGB sensor. Then we set correction to KP times deviation. Next, we calculate dynamic base power as max base power minus slowdown times the absolute value of correction. Since this computed value can go outside our allowed range, we clamp it so it stays between minimum base power and max base power. Now we calculate the individual motor powers. We set left power to clamped power minus correction, and we set right power to -1 times clamped power plus correction. Next, we clamp the left motor power so it stays between negative max base power and positive max base power, and repeat the same process for right power, and finally send those two values to the motors. And that's it. Our block program now recreates the same high-speed line follower logic from the Python version. If you want to grab the full program, you can find it on the new Learn as You Explore hub. The link is in the description. I'm adding new free learning resources there regularly. Here's the high-speed line follower in action. Thanks for watching today's project. I hope you had fun building the program with me. Happy programming, and I'll see you in the next one.